Hello, this is Dr. Hassan Abdullah with the course Complexity and Analysis of Algorithms. So, the topic which we are covering is sorting, and the subtopic within sorting is non comparison based sorting. So, the lecture is 8D. So, we have covered up till now comparison based sorting. Comparison means that the numbers are sorted, there has to be certain comparisons, right? If we compare every number with every number itself, then that results in order n square time, which is not desirable. So the best which we have done and we can do in comparison based sorting is order n log of n. We cannot do better than this, right? So then there is another class of sorting algorithms which are not based upon comparison. They are called as non-comparison based sorting, like reduction sort, like bucket sort, okay? And there are quite a few others also. So these sorting algorithms not directly compare the numbers which are sorted, but they are based on the specialized properties of the data itself, like the range of the numbers or the digits of the length of the numbers or the position and so on. So these sorting techniques, which are not based upon comparison, they can perform sorting with, say, for example, order n plus k, where k is the range of numbers. So we should not be getting very excited that so we have almost linear sorting techniques, right? Instead of doing order n log n. But the n log n sorting comparison based techniques, they are very diverse, right? Because they can be used to sort numbers which can be compared. But that is not the case for non-comparison based sorting. So non-comparison based sorting has its own application domain and has its own limitations. And this is what we will be discussing in this video. Thank you very much. So this course uses the supplemental material available at easymcq.com/go-get. So this is basically a personalized learning management system. Why it's personalized? Because you can set your pace of learning and the level of difficulty, and you can also have your own route of learning. So that's why I call it personalized. And you can of course perform setting of the interface right over here. You can set the interface, and that will enhance your learning experience. So that's personalized. And you can have personalized exams which you can do, select the topic, select the subject, and the solutions are given to you, it's graded, and the results are analyzed. So these are the videos which will show you how to do all of this. And these videos for using this learning management system, these videos are available on my YouTube channel. The videos of this course and other courses such as data structures, databases, artificial intelligence, machine learning, and so on, they are also available on my YouTube channel. So all you need to do is go to YouTube and type my username, basically type my name, which is Dr. Hassan Abdullah, and you will be taken to my YouTube channel. So these are the topics which are included in this course. Right now we are at the topic number 8, which is sorting. So let's move on to the supplemental website. So we are at the supplemental website, and at question number 16. So first 5 questions were in lecture 8A, and then next 5 in lecture 8B, next 5 in lecture 8C. So now we are at lecture 8D. So we are at the starting from the 16th question. So the question is, what are the basic non-comparison based sorting algorithms, the basic ones, and how do they work, their time complexity, and their pros and cons. So I've tried to like squeeze 3 questions into one question. Okay, so those non-comparison based sorting algorithms are counting sort and reduction sort and bucket sort. So let's look at them and things will become clear. So what counting sort does is that counts the frequency of each distinct element. So in your list, say for example 5 comes 3 times, 6 comes twice, other numbers come only once. So that's the frequency of each distinct element, and based upon this distinct frequency, the numbers are placed in their correct position. Okay, and if you want to go into the details of counting sort, you can go to the course data structures and algorithms, and there is a whole topic on non-comparison based sorting. So the best case, the average case, and the worst case time complexity is order n plus k, where n is the number, okay, and k is the range of the input values, right? So for example, if the numbers are 5, say for example, if the numbers are say for example 10 numbers, and the range of the input values is up to 100, so then k is significant as compared to n. K is like n square. So that's a limitation. Okay, that's a limitation. So it works extremely fast for small range of integers. Extremely fast. How come? Because then it becomes order n. Cannot sort faster than order n. Must have to look at each number directly or indirectly. So they're extremely fast and they're stable also. So the relative order does not change. Okay, so let's move ahead. Then is the radix sort. So the radix sort is again have the best case, average case, and the worst case is order n of k. And what is k? K is the number of digits in the number. K is the number of digits. So how does radix sort works? Again, it is available on the data structure course. It processes the digits of numbers starting from the least significant digit, right? Then uses a stable sub-sorting algorithm, like say counting sort, and arranges the numbers, right? Arranges the numbers based upon the least significant one, then the next one, the next one, and so on. Okay. So basically, what it does is that it can sort large data sets of integers or strings, right? And it avoids comparisons. There's no comparisons, right? Because comparisons can result in a time complexity between anywhere from n squared to n log n. This is order n. And k is the number of digits. So we say, for example, if we have 1,000 numbers or a million numbers, so we will not have a number with million digits. We'll have 4 or 5 digits, 6 digits, 7 digits. So this is very fast. K is insignificant as compared to n over here. So it sorts elements digit by digit using a stable sorting algorithm for each digit. And it works for integers and it works for strings. Okay. But can be inefficient for large ranges or floating point numbers. Why? Because the value, this k, it does not remain constant, right? So if we have a million numbers and we are looking at floating point numbers which are also in the range of say half a million or say 100,000, so then the impact comes at the time complexity. Then is the bucket sort. So what happens in bucket sort? I have a very nice picture over for you. So what happens in bucket sort? Divides the range of input values into smaller buckets, okay, and sorts each bucket individually. So numbers are placed in a bucket as per the range, and the sorting takes place. Now the bad thing is that it is time complexity. Best case is order n plus k. Average is also worst case is order n square, because if your bucket sizes are not matching, so to say, with the numbers, the distribution of the numbers, so you start putting in sub multiples of the input size into number of buckets. So if like if it goes like n by 1,000 or n by 100 goes into a bucket, so then it's not a constant thing. So that results in n square time complexity. So this works when the input is uniformly distributed. When it is uniformly distributed, then sorting within a bucket, that takes not more than order n time, right? And can achieve linear time complexity for uniformly distributed data. Of course, if the data is skewed, then it doesn't work. And for that to work, you should have knowledge about the distribution of the input data. Okay, so if it is not uniformly distributed, then it will result in order n square time. So these are the numbers, and they are placed in the bucket, and you see this results in stable sort. And these and if I use a stable sorting sorting technique here, right, then you can see that it results into a sorted output. Okay. So compare and analyze the time complexity of 3 basic non-comparison based sorting algorithms and their application domains. So again, we have counting sort, radix sort, and bucket sort. And let's look at the answer. So this we have already looked at. So when we have, what is the application domain? Counting sort integers or with a small range, because this thing over here, this small range, this k actually kills the performance. Okay, if the range is not proper, then it will kill the performance. Okay, such as sorting ages. So ages, like, is there are hardly age more than very few which are in 3 digits, usually in 10 digit. Grades are like two alphanumeric characters, you can say, like an alphabet and a symbol. And when the range of input values is known and it's small. So counting sort efficiently sorts data by counting the frequency of each element. So you know the use case now. Then is the radix sort that we have covered in the previous question. Sorting integers, very nice, strings, or fixed length data. So large scale data processing, right? Numerical sorting and external, because you see that it is order n plus k, and this k is this. What is this k? K is the range of numbers. K is the range of numbers, and when this range is less, right, then it works fine. Radix sort is then very fast, because now for bucket sort, we have this time complexities here, but the uniformly distributed data. Otherwise, it results in a chain or a lot of. So what I'm basically trying to explain here, let me draw for you. So if we have this, say for example, we have age here. Okay, pardon my writing. And this is the frequency of age. So if it is skewed like this, then it is not good. Okay, it could be Gaussian also, but still it is skewed in the middle. It's not good. So this is asking for a uniform distribution, which is very hard to get. So it's like something like this, uniform distribution. So if we have uniform distribution, then this is fine. This is nice. But this is not good. This is also not good, because this can result in order n square time. So it must have uniformly distributed data. Okay. So what are the algorithmic differences between comparison and non-comparison based sorting? So it is the sorting mechanism itself. There is obviously there is no comparison in non-comparison based sorting, and for example in bucket sort, radix sort. So then is the time complexity. The best case time complexity of comparison based sorting does not matches that of non-comparison based sorting. Space complexity can be an issue. Suitability for different data types. So non-comparison based don't work for, or difficult to use for, the entities which cannot be compared. And then is the performance in different scenarios, and then the stability and adaptability. We'll talk about it. So the sorting mechanism: quick sort, merge sort, bubble sort, insertion sort, and so on. They are based upon comparison. The algorithms repeatedly compare pairs of elements and reorders them. Okay. However, in non-comparison based sorting techniques like counting sort, radix sort, and bucket sort, do not compare elements directly. Okay. They rely on the specific properties of the elements, integer values or digit positions, so on. So basically, effectively, there is without performing comparisons, right? Time complexity of comparison based is best is order n log n, and worst case is order n square. But non-comparison based sorting achieve a linear complexity. Okay, and for example, when k is the range and the range is small, o n plus k is o of n. Okay, space complexity of comparison base is order n, right? For in the case of merge sort and with recursion quick sort, it is order log of n, right? In the best case. But for non-comparison based sorting, the space complexity is order k, right? And for example, radix sort requires additional space, which can be order of n. Still, it is better or compared. So in terms of time complexity, non-comparison is better, but they are taking up space, so there's a trade-off. Okay, suitability for different data types. Comparison based sorting for which comparison operation can be defined. If comparison can be done is defined, then of course you can perform comparison based sorting, like using sorting strings and floating point numbers. But non-comparison based sorting algorithms, okay, they look at the discrete properties of the data itself, such as the digit positions, fixed value ranges. Okay, so that is so there must be bounded range, right? So these are the limitations or the application domains for non-comparison based sorting. So in performance, of course, they outperform the comparison based algorithms, where the input data has a limited range or well-defined structure. But comparison based algorithms like quicksort, merge sort are more versatile, which the non-comparison based are not. So when the data lacks specific properties, okay, that are there in the non-comparison based algorithms, okay, then we use the comparison based algorithm. So we should be aware of all those things. We should know our data stability and adaptability. So these are new terms. Adaptability. So stability we have already discussed a lot. Adaptability is how an algorithm performs under different input conditions. So if the data is already sorted or nearly sorted, quicksort is a disaster. Okay. While for non-comparison based algorithms like radix sort maintain consistent performance irrespective of the data is sorted or it's not sorted. Why? Because there's no comparison, right? So kind of winding up this. So how to determine the efficiency of a sorting algorithm in different scenarios. So we have covered a lot of these things: best case complexity, average case, worst case, space, stability, adaptability. And let's look at practical performance considerations, which we'll do more in the next topic. Practical performance considerations on the constant factors. What are those constant factors? Like input size, the hardware, right? Because depending upon the hardware, the performance of the machine will vary, and the performance of the algorithm can also vary. For example, quicksort often outperforms merge sort in real world users. Why? Because of the smaller constant factors. We don't look at those constant factors when we do a complexity analysis. That is not bad because we are looking at from an abstract perspective. We are looking at the big picture. But when we come down to practical performance considerations, then we need to look at these things. Okay. And scalability is that as the data size increases, okay, so of course, order n log n complexity like quicksort and merge sort scale better as compared to order n square algorithms. And same is true for the implementation point. You see, for example, how one implements Fibonacci numbers. They, if not properly implemented, that results in order 2 power n time complexity, which is non-polynomial. So we have to look at the scalability from the algorithmic perspective very carefully. All right, so we that topic ends. So that's all. Now we will start with the next topic, which is benchmarking and the use cases.